Right, we're in Windows kernel world again. It's great to be here with Chris Stevens.
Yes.
Tell us a little bit about yourself. What do you do?
So I've been at Microsoft for 3 years, and I joined the kernel team. I owned the registry for about a month, and then they put me to the boot environment.
Okay.
And so I learned the ins and outs of 16-bit code, assembly, and some low-level stuff, and put that to good use throughout Win 8.
Okay.
So I'd like to start off like a little introduction of where we were in Win 7.
Perfect.
And so kind of what you need to understand about the ecosystem of PCs is that since 1980, PCs have been booting starting in 16-bit. 16-bit code, real low level, nobody really wants to develop in that. And so now, since the mid-90s, when Intel created the EFI, which stands for Extendable Firmware Interface, and which has moved on to UEFI,
okay.
Unified Extendable Firmware Interface, we get a firmware environment that developers, driver developers, or your RAID developers can write in what you might call native code. So if it's a 64-bit PC, they can write in 64-bit code. So they don't have to write in 16-bit to get their option ROM up and running.
Great.
So, a little bit of background of how Windows booted in this legacy environment will kind of give us some motivation of why we changed. So, in a legacy environment, you'll have your 16-bit code in the firmware scan the disk. And so what it'll find on the disk, it'll go to the MBR, the master boot record, and find the active partition on the disk and jump to it. So in the legacy world, that active partition will be some NTFS volume, which you might call the system volume as opposed to the OS volume. In there, there's some 16-bit code that we call ntfsboot.com. And so Windows will write that to the first block of the NTFS volume, and what it does, it looks for whack boot MGR on the volume. So remember, we're in 16-bit code, so we can't access that much memory. And so what this NTFS boot code does, it loads boot manager into memory, so this is our physical memory, at address 20000, which is 128K. And keep in mind we have some memory, some video memory sitting at, or general firmware memory sitting at 640K. So our boot manager has to be at max 512K if you do the math. So what this ntfsboot.com will do is load the boot manager here going up. Now, the problem that we were seeing in Windows 8 on some servers is that there's a stack here going down. So on some large servers with large disks, there is option ROMs. There are option ROMs that are using this space. And so when we were innovating and adding things to our boot manager, we were creeping up to a size of about 400K, and we were running into problems. So we'd be booting, and all of a sudden, well, we'd reset because we would have corrupted the memory of some other option ROM.
Okay.
And so that's a huge limitation as we're packing more and more features into our binaries. So first motivation to move away from legacy BIOS. Now, what is this boot manager? So this boot manager is actually two binaries stuck together. So it's more 16-bit code that we call diskboot.com. Now you'll never see diskboot.com or ntfsboot.com as a binary on the system. They're baked either into the boot manager or into the file system code. And then the second half of this binary is a compressed version of a PE image, which we call bootmgr.exe.
Okay.
And so the purpose of this 16-bit stub here, it will get executed or jumped to from the NTFS code. And what it does, it'll decompress bootmanager.exe to at memory starting at 1 megabyte.
Okay.
And so it'll jump into protected mode, enable the A20 gate, some really gnarly stuff, and reload boot manager at 1 megabyte. And after that, it'll reload boot manager again to the preferred base address, which is at 4 megabytes. So as you can see, we've loaded it once, twice, and a third time. Not very efficient, and kind of motivates a re-architecturing of it all. So that's the initial stack, and then this is a 32-bit binary. And so after boot manager is up and running, what it will do, if you're familiar with Windows, is load winload.exe. And so that's the next binary in the boot chain, and winload will load the kernel. And so that's where we are. And so in that timeline, the boot manager can either jump to a 64-bit copy of winload, or a 32-bit copy of winload, or it can jump to, if you really want to boot XP, NT loader, or it can even load a Linux loader if it wants to, because it just needs to load stuff into low memory and then jump to it. But in this world, say where we're loading a 64-bit winload, what winload will do is it needs to read all of the boot critical drivers and the kernel off of disk. Now, in this legacy BIOS world, the disk services, you might know them, int13, and graphics services int10. All those legacy interfaces with BIOS, those run in 16-bit mode. So when we're in 64-bit mode and we need to read from the disk, we have to thunk down to 32-bit mode and then jump again to 16-bit. And so we're doing all of these transitions. And then as a result of 16-bit, we can only read so much at a time off of disk because the buffers are only so big. And so if we're reading a 2 megabyte file, we're not reading it 2 megabytes at a time. We're not letting the firmware optimize. We're saying, give me 64K at a time, or whatever the increment is. And so that is also another motivation, is that we're doing this extra overhead to switch the processor mode, coming in and paging on, paging off, and that is slow.
So before you continue,
Sure.
We're talking about how it was.
Yes.
And I want to make it clear for people to understand, how much of this was involved with really slowing down boot for human perceptible levels? In other words,
Sure.
There's a lot of other things that have gone on to speed up boot, which
Right.
we're going to learn as we progress in this great conversation. I won't interrupt you too many times.
Yeah.
But I just wanted to make it clear that this is a part of what made it slow. And if you could explain to people how slow it made it when you found out doing your research and your re-architecture.
Right. So this, really the 16-bit code, hard to innovate in, and what we will talk about soon is post time. So the firmware post time, for the firmware to get up and running to jump to this MBR on legacy systems, 10 seconds, 13 seconds.
Ouch.
On your server, it could be a couple minutes if you have a terabyte of memory, but that's not the client case, right?
Understood.
And so it's 10, 15 seconds. And so when you see a Windows boot time of a minute, almost 20% of that, is the firmware.
Got it.
Now these boot binaries, we didn't really shave off a whole lot of time out of the boot manager code and the winload code. There's incremental steps here, but it's still just kind of heinous to look at. And so winload is churning a lot, trying to read binaries off of disk. And so what's helping speed that up is that we don't have to do it in small chunks. We can do it in larger chunks with UEFI allows. So we get faster throughput on the disk, and that kind of lost my train of thought. But either way, so that's that kind of motivates changing to UEFI.
Great.
So that's the old world, and we jump to the kernel, and well, the kernel's the kernel for now. So now the new world. So what did we get with UEFI? And so what were kind of the goals there? And so if you think about that 13 to 20 second post time on your classic legacy PC, that's not really a good consumer device experience. When you start up your TV, well, you click the button, your TV's on, right? And now when we're getting into tablets and touch screens and the PC's everywhere, it's on your TV. We want a consumer device experience. And so what we had the opportunity to do with Windows 8, working with the BIOS vendors on UEFI, is to really speed up that post time. And so we made a Windows 8 requirement that post time is less than 2 seconds. So if we're going from 20 seconds to 2 seconds. Now, if you want to look at it from a marketing perspective, that's 13 seconds that our partners, the OEMs, were losing of advertisement time. So they would display their logo during their post time and hand off to the OS. And part of that handoff was switching into text mode, which would erase the screen. And so then Windows, if you remember from Windows 7, it would display those, what we call it, the fireflies, the flag that came in.
Yes.
Right? And so there was some time of OEM branding and then the OS branding. And so now if we give the OEMs 2 seconds, but we have the rest of boot, that's not going to, that's not a good partnership, right? And so the first feature that I'm going to talk about for UEFI is co-branding. And that gets into how graphics works. So in the legacy BIOS era with Int 10, the firmware would hand off to us in text mode. And so we, in the boot environment, don't know a whole lot about what monitor's plugged in, what the native resolution is of your screen. And to simplify things, we just switched into one of three modes. 1024 by 768 was preferred. And so...
Black. Can you use the black one?
Oh yeah, sure.
It just comes better on the screen.
So we had text mode handoff, switching to 1024 by 768. And so here there's a screen reset. So anything that the OEM had written to the screen is gone. And then we have Windows branding. Now, in UEFI, we don't have this switch to text mode before the UEFI code hands off to the Windows Boot Manager. And so what we get is that we'll get the native panel resolution, so the preferred 1366 by 768. This is UEFI. We'll hand off, and we'll stay in 1366 by 768 in Windows with no screen clears. And so what that allows us to do is have the OEM draw a logo. We'll not clear the screen. They'll tell us where the logo is on the screen, and then we'll use it. And so now you get, OEM logo, all the way up to here, your high-res driver comes online, and we'll do a fade. And because we know where the OEM logo is on the screen and how big it is, we can fade it out. And so if you're digging into your ACPI specifications, if you look at the BGRT table, the boot graphics resource table, that is how UEFI and the OEMs communicate to Windows where this logo is and how big it is. Okay. So that's one feature we added to get that, to get towards that 2 second post time. We had to satisfy our partnerships, and so we get this co-branding experience, right? So that's number one feature that our UEX team really wanted.
Well, it's important.
Yeah.
Right?
No, it's certainly important, and it definitely made our partners happy and drove us towards that 2-second post. So now, one of the big things that was slowing down post time, even on UEFI systems, was the enumeration of USB devices. That takes 1 or 2 seconds alone to spin up USB devices. And so now if you think back to your legacy or your classic PC experience, you not only get your OEM branding during the firmware post time, but you have some options to hit F2 to enter this BIOS menu, or F1, or delete, or escape. Pick your button of choice. And now to press those keys, you need a keyboard. So you need to enumerate USB. Right? So how are we going to go about speeding up post time, getting rid of USB, and satisfying this need for users to sometimes get into their firmware environment to reset default settings, turn on virtualization, or change the boot order. Right? So what we developed was something that we put into the UEFI spec called
we need a new marker.
Called OS indications. Blue might work?
Yeah.
OS indications. So you'll find this in the UEFI specification. And paired with that is OS indications supported. So these are each 64-bit values that are stored in UEFI non-volatile RAM. So on UEFI there's a namespace of variables that are stored across reboots, non-volatile RAM. And in the global namespace there are these two variables. So the firmware can access them, the OS can access them. And so in the OS indications supported, the firmware indicates to the OS which of these indications it supports.
Okay.
And then in the OS indications variable, which is owned by the OS can ask the firmware to perform an action or to enable a feature. And so the first one, and the only one that we have now, is there's a bit that says go to the firmware UI. And so from up in Windows, you can go to the advanced boot options menu. If you hold Shift while clicking Restart, that'll get you there. And you can go into the troubleshooting menu and click go to the firmware setup menu. And so that'll set this bit, reboot, and stop at your firmware menu. And so you didn't need to press a key in those 2 seconds. So now you're saying, well, what if I have my PC is so broken that I can't get up into Windows to go to this menu, right? So that's where Windows 8 is more heavily dependent on Windows RE, the nickname for the Windows recovery environment. And so we offer the same entry point into the firmware menus by going to WinRE. Now, so say in a world, or say you have a bad driver, you get some new device, you add a new video card, and you install the new driver, reboot, and it bug checks. Not harping on video drivers, but it bug checks your system, and you can't get up to Windows, and so you need to go change something in your firmware to maybe toggle back to the inbox graphics driver. And so what we'll do is after 2 failed boot attempts, so 2 bug checks early during driver initialization, we will automatically go to WinRE. So if you remember in Windows 7, after a failed boot attempt, we would show an ugly black and white 80 by 25 console screen, not your consumer device experience, and give you an option to start Windows normally, and you'll bug check again, or go to this recovery environment. But we made it seamless, so you'll go to the Windows recovery environment, and to your average user, you don't know the difference. And so you'll get to the same menu, give you the same advanced options, or even try to repair your problem automatically. And so that's how we got away from needing USB, by building a larger system around recovering your PC, imagining what problems a user could get into, why they would need to go into the firmware settings. And so you can imagine, the future, the next steps where this OS indications has your whole array of firmware settings, and you don't even need to go into the firmware to turn on, say, virtualization if you want to enable hypervisor. Right? You just click a button in the OS, you reboot, And the firmware reads that variable, flips a bit, and you go back up. You don't need to go into the firmware menus. And so that's kind of where we were going with that. And we worked with our partners in the ecosystem and the UEFI forum to get that into the spec.
Great.
So, I guess backing up a bit, as you might have recalled, the architecture for booting a legacy system, we were reading 16-bit code and 32-bit code and 64-bit code. So I think it's worth talking a little bit about how UEFI works before we get into the other features.
Okay.
And so the handoff, or this chain of events, will start with the UEFI boot manager. So on a 64-bit system, that is 64-bit code running. On an x86 system, it's 32-bit. On an ARM system, it's ARM code. So there's no 16-bit, no legacy code here. And this will go through a set of steps to figure out what device or OS it should boot. Now this is all defined in the UEFI spec, but the brief overview, it'll look at a few things. It'll first look at one of those NVRAM non-volatile global variables called boot next. And this will tell it, it's kind of like a one-time boot into that device or that OS. And if there's nothing there, it'll look at what is defined as the boot order. So this is a set of 16-bit values, so on, that correspond to boot entries. So when we see boot 0000, we'll go look at this entry and see what is that device or OS that I need to boot. And so those are the steps that the UEFI boot manager is going through.
Okay.
And so when Windows installs, it will place itself first in the boot order. Otherwise, you're going to have to go through trying to network boot or trying to USB boot. And that fast on experience isn't going to be there if we're sitting through various boot options. So Windows installs itself first. And so in this boot entry, we will give a path to our boot manager, which we call in UEFI boot mgfw.efi.
Okay.
Now that is sitting on that line's not going to come out, but it's sitting on a FAT32 partition on your disk.
Okay.
Why FAT32? UEFI is only licensed to read FAT32, so they can't read NTFS. And this is the unprotected system partition. So if you're thinking of in terms of BitLocker, this data is not encrypted. So the UEFI code can access it.
Understood.
Otherwise, UEFI doesn't know how to read BitLocker volumes, so it's open. And then you have your NTFS OS volume. And so this will transition to the boot manager, and the boot manager will jump to winload.efi, maintaining bitness. So 64-bit, 64-bit, 64-bit. So as part of this handoff, what the UEFI boot manager passes to our code is two things: an image handle and a system table. So these are standard EFI application entry arguments. So this image handle is a handle to yourself, so you can figure out who you are, what device you're on, etc. And this is the system table, which stores the boot services and runtime services. So, if you think back to int 10, int 13, int 16, all those legacy interfaces, these boot services are the new interfaces. And so in here you'll have allocate memory, free memory, connect all your devices, locate a protocol. So now what are protocols? So if you have a handle, you can search for protocols that are advertised on that handle. And one of those protocols is, say, the block I/O protocol. And so the block I/O protocol has read blocks, write blocks. And so that replaces your int13 reading from disk. And we can pass that protocol as much, a big a buffer as we want and request as many blocks to read as we want. We don't have to, do it 64K at a time or whatever.
Okay.
And so that's, where we get these interfaces from UEFI on that transition. And we preserve them all the way through. And one of those protocols, for instance, is the network protocol. So DHCP 6 or DHCP 4. And what we use that for is a BitLocker feature. Now, I'm not the security team, so I'll briefly talk about that. But it's called Network Key Protector. So think of a work environment where your IT manager has locked your system with BitLocker, and Windows Update runs. It's Patch Tuesday, and you're away from the office, and your system needs to reset during updates. You walk back in the morning, and it's been sitting at a BitLocker key entry screen in the boot environment for 12 hours. Right, so we're wasting energy, and your computer can't fall asleep at this menu because it's in the boot environment, and it's kind of annoying. Right, and so what we have with this network key protector is that the IT managers can set up a server, and so when your system reboots and it has BitLocker and it has the network key protector enabled, it can use these DHCP 4 or DHCP 6 protocols to go over the network, talk to the authenticated server, get the key, and boot up. And then it can go back to sleep, or doing whatever nightly jobs you might have had running. Now that wasn't possible in the legacy BIOS environment. So once we forked to booting from a disk, we had kind of buried the network stack. Now you can PXE boot on a legacy BIOS system, but going the disk route and then firing up the PXE stack just wasn't something that Windows had ever invested in.
Okay.
And so this was pretty easy, pretty seamless to do.
Okay.
So that's kind of another big feature that we have in Windows is this network key protector unlock in the boot environment. So the next step, after we use all these runtime services and boot services, we will exit from UEFI. So at one point in WinLoad, we call exit boot services. Exit boot services is a UEFI boot services routine. And what that says is UEFI, the OS is now going to own the system. So clean yourself up. And what does that entail? Well, UEFI might have, or has its own IDT, GDT, its own memory map, all that stuff consuming memory. And after we call exit boot services, we're free to now use that memory. And so if any device needs to be put in some state, or anything needs to be cleaned up, that's the time for the firmware to say, okay, we're done. The OS is going to own the system. Now, there's some, fun things that go on with memory in this time. And so, to get a little low level here, we can talk about virtual memory paging, how that's working. So, on the 64-bit system, UEFI is required to map all physical pages one-to-one in page tables. So if you want to access a physical address, well, you can just access that physical address because it's guaranteed to be mapped one-to-one in the paging structure, and including all of these services. So these are all mapped one-to-one. Now, the boot manager runs on top of the UEFI page tables. So we have UEFI page tables. But the OS And WinLoad can't run on the UEFI's page tables because we're going to call it execute services. Right, so we can't like rely on those existing throughout, and having everything mapped one-to-one is somewhat inefficient. And so what we do is we build new page tables for WinLoad. And because we need to keep interacting with these boot and runtime services, in our new page tables we also map the UEFI services one-to-one. So here we have OS page tables, but with UEFI. Now, this ran into a problem on 32-bit systems, so your ARM systems or your x86 Intel SoCs. Why? Well, if you look at a system that has 2 gigabytes of memory, so 2 GB, or I guess let's go with 4 GB. And the half line at 2 GB. So, on a 30-bit system, Windows will take its kernel virtual address space and use the top 2 gigabytes. So, when we are mapping boot critical binaries, the kernel, into this kernel VA space, we need to pick a memory address that's up here.
Okay.
So, the old algorithm, it would take the physical address and OR it with hex 80 million. So, VA equals PA ORed with 0x 80 million. So, that was a very deterministic virtual address. So imagine we're using physical address 0, the first page, and we wanted to map it right here. So we have the OS data because of this algorithm. But in the UEFI world, it's very plausible that you could have boot services already mapped at 2 gigabytes. Why not? We don't restrict the range in which UEFI can allocate their data. And so, without a change in Windows 8, we were going to fail, potentially, perhaps randomly, if UEFI was randomly locating boot services on some machines. So we needed to wipe this kseg kernel segment addressing problem. Now, we do have, in this boot environment, we have a full, almost, or a mini memory manager, which we know which virtual addresses are free, we know which physical pages are free. And so what we had to do is, instead of just doing this quick and dirty OR operation, we had to go find the free VA. And so that basically solved this problem. But there were some other issues. And so not only did we have this, we had some other fixed virtual address mappings. One of them is this neat trick that we use to modify PTEs. So, and we call it the self-map range. So if you think of a 32-bit page table structure, and you have your PTE out here, if you need to modify this PTE, you'd have to map this page into a PTE. So if you have some PTE address pointing at this page table, you'd need, say, some other PTE that pointed at this page table to be able to modify that PTE. That quickly gets complicated because you have a whole mess of pages and various pointers from PTEs back to PTEs. So we don't do that. All we do, it's pretty elegant, is we just set a simple self-reference. So pick a PDE entry, and all it does is cycle back to this. So when you're looking at your virtual address, you can take this 16 or this 10-bit offset twice. and then use the page offset to get to the PTE.
Hmm.
So you have your VA is composed of 12 bits, and then I guess it's 9 or 10 and 10 in a PAE world, or 10 and 10 in a 32-bit paging, or either way. You take these two would be identical, and you'd loop and loop again, and then get your 12 bits page offset. And so this location was fixed.
Hmm.
And so we always needed the virtual addresses from 3 gigabytes to add 4 megabytes to that, because that's where we use the self-map region. Well, we can't map UEFI services one-to-one if they're sitting at 3 gigabytes if we're going to need those VA ranges. And so what we had to do was dynamically allocate this self-map region. And to do that on, say, 32-bit, is you need to pick a free, virtually free 4 megabyte region that you could use that UEFI was not occupying to do this reference. Now, on top of that, you had to physically allocate that 4 megabytes.
Yep.
Because at any point, UEFI could have allocated something out of the backing physical pages, and then you need to map that one-to-one, and well, you've just occupied all of that 4 megabytes with your self-map, so you can't map it. That gets a little gnarly, and there's a way to fix it, I think, which we might attempt in future.
Nice.
But what we have is working now.
Great. Absolutely.
So that kind of gets into the how UEFI boots up to the kernel, kind of the differences between legacy, and so there's a few more features we could talk about if there's time.
We can probably squeeze in one more.
Sure. So let's see. So so one thing that you get with UEFI, which is kind of a big selling point, is something called secure boot.
Hmm.
So you could probably have a whole couple hours talking about secure boot, but I'll briefly mention it. So you have again the UEFI boot manager. And so this is, since it's a fully running 64-bit app, etc., that can be serviced easily, it can maintain a root of trust for the system. And so what it does before it launches any root application, it'll look in its database for that signature. And so the Microsoft and the OEM will make sure we fill out that signature with only trusted information, and then turn on secure boot. And so at that point, this boot manager will only load a certain set of binaries that have the signatures. And so that is the firmware trusting the boot manager, which we didn't have before. So when we were in 16-bit code, well, there's no way that the firmware could trust that 16-bit code because there weren't signatures in the code. They weren't proper binaries. And if you think about rootkits, many of those attacked that 16-bit code I was talking about. Right? They would infiltrate the MBR or the first sector of the file system and just inject code, launch to something else that roots your device, and then come back and boot Windows normally. The user doesn't know about it. And so with this root of trust, that this is a full PE image, and that you can have some servicing here, and there's a database or room for a database of signatures, we can make sure that we trust this transition. And that's the key point. After that, Windows can trust itself by doing verification checks on WinLoad and the kernel and all the drivers.
Mm-hmm.
And so another feature on top of that is the early launch anti-malware driver, which is the first piece of third-party code outside of the UEFI boot manager to run. And so what that is allowed to do is have a white and black list of trusted third-party boot drivers. And so it can say, I trust this one, I don't trust this one. And so it can communicate with the runtime anti-malware driver to say, either this one didn't load because it's got a bad signature, I don't trust it, or whatever happened. And so that's kind of this whole root of trust all the way through the system that we built because we could start here with UEFI.
Great. Excellent. So, it seems that, with the modern boot, you guys are fully based on UEFI, and we talked about UEFI in the Vista timeframe,
Yes.
where we started the boot. You know, we had interviews on Channel 9 where we
Right. With Jamie and Andrew.
You got it,
Yeah.
man.
So
Is
that
that
was-
why? You were in college then, I'm
Yeah.
assuming. Yeah, look at
I
that.
didn't know what UEFI was.
Yeah.
So that was, developed in the Vista timeframe for Itanium system, which were UEFI only.
Mm-hmm.
So, we had to go that route. And on Win 7, we do support UEFI and Vista, but Win 8, it's a requirement. We still support Legacy in Windows 8, so your old PC will work. But, you get these added security things. You get that real, consumer on-off experience with Windows 8 and UEFI.
Absolutely. You guys have done tremendous work. I mean, the resume from standby, which is a form of boot, but not really.
Yeah,
But
the hybrid boot.
The hybrid boot.
Didn't even
which
touch
we're
upon
gonna,
that.
I think that's something we're going to have to come back and spend some quality time on, because hybrid boot is incredibly interesting,
Yeah.
especially in these modern
That's
devices.
a full hour itself.
So we'll do that.
Yeah.
And so I think this is giving people a really nice low-level view of
Right.
what it takes from
To
a user's
bootstrap the
perspective.
system, yeah.
Oh, it's incredible, man.
It's all the magic that goes on underneath.
It's amazing, and you know what? The code's running super fast.
Yeah.
So nice work, you guys. You wrote some tight code. So cheers. We'll come back and talk to you about hybrid boot.
Okay, thanks.